All right. Good afternoon, everybody. Thanks for joining us today for our final webinar of this year's STEAM Timber. It's been a great month with lots of great content, and we're happy to have Nick Westerberg with us today to round out the month and give us a lot of great information. So thanks ahead of time here to Nick for doing this for us. Before we get started, just a couple housekeeping items. Again, this is the third webinar we've done. We had two previous to that. Last week, Adrian did one on actually using our DMS software to generate a STEAM report. That is on our website, so if you missed it, you can check that out. It's in the webinar section and in the on-demand education portion of our site. And before that, we had Kelly Paffel, and he was talking about detecting leakage on internal valves. And so that was a really informative webinar as well. And again, that recording is up there. So if you're on here today, obviously STEAM is of interest to you. So we've got those other two resources that you can check out when it's convenient for you. So just like we recorded those webinars, we're going to record today's, so you can check it out again later if you've missed something, or if you have to hop off early, or if you've got colleagues that couldn't make it. We will make this available either later today or early tomorrow. We'll have it up on our site. So keep your eyes out for that. We also invite you to ask questions throughout this presentation. You can do that just typing them in. You've got the little menu bar on the side there, so you can type questions into us throughout. I'll be tossing those over to Nick as it's appropriate, or of course we'll have some time at the end for question and answer. If we don't get to all the questions, we'll certainly be sure we get any questions asked to Nick, so he can be in touch with you offline. That way we keep our time to the 1 hour. So in the spirit of that, I will turn the screen over here to Nick. So bear with us, just a quick little pause here while we switch screens. And Nick, I'll let you take it away.
Excellent. Okay, let's make sure that this comes up properly, and we will hopefully get everybody something to look at.
Looks perfect.
Is that being displayed properly, Maureen?
It is. So we're good to go.
Excellent. Well, everyone, Steam Timber is that time when we get to fire the systems back up and get ready for the fall and the winter. Whether you're at a college, an institution, or an industrial processing facility, not everyone uses the full load that they're capable of producing in their boiler up until the time it starts cooling off. And one of my great examples is a local college. When the college kids come back and enter college here in the northern part of the United States, it starts cooling off and we start firing up the dorms. And boy, does it create a tremendous amount of opportunities inside the STEAM system for those of us in maintenance and in the STEAM world. I'm going to talk today about steam trap types, steam trap selection, troubleshooting, and then some of the equipment that we use. The fun part for me is all the great professional associates I've met in the STEAM world, and those that have a lot more knowledge than myself. I am a 57-year-old defensive lineman that's been hit really, really hard in my younger football career. So while not the sharpest tool in the shed, I love and I'm passionate about steam systems and pumping equipment. And you'll see that at the end of the presentation. I'm going to share some information that you would have the ability to take advantage of because you jumped on this webinar today. So if you don't mind, I'm going to go ahead and start my presentation. I'm going to look at what it is we're trying to do with steam traps. And I'm not going to go into the real fundamentals although I am going to show you some of the different trap technology section views so you get to see what the actual steam flow, condensate flow looks like through these devices. In steam trapping, properly functioning trap should automatically remove condensate from the heat exchange area and promote efficiency. It should retain steam in the space. We're trying to use the latent heat of vaporization, the BTUs that we actually have in the steam. We would vent the CO2 and the non-condensables, so carbon dioxide non-condensables, which affect the heat exchanger efficiency. If we cannot get the air and the non-condensables out of the steam space, then it's more difficult for us to get all of that space filled with steam and actually be able to extract the heat and put it into our air or our lumber or our paper or whatever it is that we're processing. The other thing that we have the sometimes difficult time in our steam trap population is corrosion and erosion. I recently had someone come to me with a dislike of a particular trap technology and said, I don't like that trap because it does not stand up in my system. And I said, can you send me a picture of where your trap and how your trap is located? And unfortunately, gang, what they had done is they had put that steam trap in a position where it was never going to be successful, meaning it was on the bottom of a mud leg that was never clean, and the steam trap happened to be that lowest elevation, and all of the garbage that was in that system ended up in that poor trap. So that trap manufacturer and that trap technology got a bad rap, if you will, because it wasn't able to process with all that garbage that they had shoved into it. A steam trap number 5 should be able to handle dirt and scale to a certain extent. We put strainers in front of trap technologies, and I want you all to know right now, please, please, please be very careful with your strainers and make very certain that you have nipples and blowdowns on your strainers. And when you touch your steam trap population, I would ask that you also touch your strainers and make sure they get blown down. It's unfair, again, to blame a problem on a steam trap when you have a strainer in front of each of your traps. And I went in and did an audit on a facility that was built in 1989, and the steam traps in the facility had never been put in with nipples and blowdown valves, and so those strainer screens were completely filled up with garbage again, and unfortunately the traps in certain portions of that facility did not work, but the strainers were never ended up being put on a maintenance schedule. A steam trap should provide long life and dependable service, and one of the things that I need you to know is that each of you have a responsibility with the steam traps that are in your facility, in your area. We become the guardians of these devices. They are built to do a great job, regardless of the color, the trap type. They would not be in your facility unless someone helped make sure and select the proper capacity and the proper technology. But we have to make sure that we do our job and that we help oversee these devices so that they get the opportunity to run to their maximum life. If you do these things, and if you pick the correct technology and you oversee these as guardians, you will end up getting maximum temperature maintenance and efficiency, maximum fuel economy, maximum performance out of the heat exchange equipment. You will end up with quick heat up of your equipment because you will remove the air and the non-condensables, and at that point you will then have the ability to completely fill that space up with steam. You will end up with reduced maintenance and labor cost. At the end of the day, there on the bottom of this slide, I want you to know that there is no perfect and universal trap. And I want you to be really careful of anybody that comes to you and tells you that their device can be used everywhere and that it is a universal device. It is low maintenance. It is low or no maintenance because there's no moving parts. Just please be very, very guarded and careful if someone comes through your door and tells you that they have the perfect trap for every application. Because up until this point, I have been doing this for quite a while, I haven't seen one of those yet. There are different traps made for different applications, and we're going to visit a few of those today. We're going to look at inverted bucket steam traps. We're going to look at float and thermostatic steam traps, thermodynamic steam traps, and thermostatic steam traps. And there are different applications that many of these traps have been recognized as being successful in these different applications and these different industries. Again, remember, be careful of that one perfect device that is suited for every application. These different traps have different nuances that allow them to be used successfully in these different applications. The first trap we're going to look at today is a inverted bucket steam trap. And if you can follow my arrow, I have some red arrows. The one thing I want you to know about these traps is they are very good devices. They have a long history. They have worked very successfully for many years, and they are a good device. But like any trap, you have to understand how they are built and how they're made, how they function, and make sure that you understand the actual pressure differential that these traps will be subjected to. And when I say that, the inlet pressure, P1, the inlet pressure on the upstream side, if that's P1, and let's just say that my inlet pressure is 200 psig, I have a condensate return downstream pressure of 100 psig. If I take my 200 minus my 100, I have a differential pressure of 100 psig. 200 minus 100 gives me 100. So this trap, let's say, has the ability in my particular application to see 100 pounds of differential. These traps have different size orifices that give us the ability to pass different amounts of condensate in pounds per hour. What we have to do is we have to be intelligent enough that we understand that that orifice is going to be chosen based on the differential pressure that we're going to see and based on the volume or the amount of condensate that needs to be processed. And I need you to know this, that differential pressure is very, very important. And I have a small story to share in that a company recently mothballed a coal-fired power plant and put in a gas-fired power plant for a college. When they selected the new power plant, they changed the pressure of the actual power generation to the campus. When they did that, they did not necessarily stop and consider whether or not the traps actually had the correct size orifices based on the differential to process the condensate load that they could see. So what happened now was that they had a large population of inverted bucket steam traps, which is absolutely fantastic because these devices have worked for years and years and years very reliably. Unfortunately, what they did not remember is that the actual capacity of those traps is predicated on that differential. And unfortunately, when you exceed the differential of the steam trap, this inverted bucket steam trap, the trap actually stops functioning. And so they actually banked and built condensate up, and they had a condensation-induced water hammer event that blew up some valving components, and they had a major incident. It is very, very important to remember that if changes take place inside the system, that you all stop and consider what exactly is it that I have in my inverted bucket trap population for differentials. And I want you to know on the top of every inverted bucket steam trap, there is a tag that will give you the PMO, the maximum operating pressure, and or a stamp with a set of steel dies that somebody will take and stamp. A 60, a 30, a 125. that number will be that max differential that that inverted bucket steam trap can actually work within. I need you to know your equipment. I need you to be able to put your hands on with a magnifying glass and a flashlight, and I want you to make sure that as you travel your campus, your facility, that you understand what those differentials are built into the steam trap, inverted bucket steam trap population that you use. It's very, very important because it also tells us what the actual capacity of this trap is. This trap is capable of operating at reasonably high pressures and temperatures. It must be protected if you're outside and you're in a colder environment, because if this trap body is processing and then you shut down for a weekend, and I was recently in Montana, and the facility does use inverted bucket steam traps, and they're changing their production schedule, and they're going to shut down over the weekend. In the wintertime, when it gets cold, if that trap body has been processing and then it has the ability to go idle during the weekend period, that condensate laying in that body can freeze, and it will break those bodies. So you need to be careful about that if you live in that environment. Limited ability to vent air in non-condensables. On every steam system, I look for air vents and vacuum breakers, and to me they're very, very important for a couple different reasons. I want to be able to get rid of the air and non-condensables so that I can fill the steam space with steam. One of the other things that I want to do, though, is I want to be able to make sure that I have vacuum breakers on my systems so that if and when a steam system goes down, whether it's intentional or unintentional, I can break the vacuum that will be formed when that takes place. And what that will do is it will act as a guardian for condensation-induced water hammer. So I'm always looking for safety-related issues, and vacuum breakers and air vents become safety-related issues. Now, I have to say that the inverted bucket steam trap is a very good device, but it has a little bitty, teeny tiny hole right on the top of the bucket where this red arrow is, and that is its ability that satisfy this particular technology with its ability to vent air. I like to promote an external air vent when someone uses an inverted bucket steam trap to make sure that we can evacuate the air and non-condensables. That way, this particular trap, all it has to do is be good at processing the condensate as it's formed. Failure mode of this trap is typically open. These traps can lose their water seal and their prime, and you may have to reprime them. It's as simple as closing the valve and allowing the steam to condense and filling that leg up, and then going ahead and opening that valve back up and letting it go. I like to check these traps, and they're simple to check with a mechanical device, and towards the end of this presentation you will see some of the mechanical devices and some of the electrical and the ultrasonic listening devices that are used to check these traps. You can literally hear these things cycle when you're close to them. That's one of the other reasons why I like this technology, because it's actually easy to check. But I need you to be patient when you check any steam trap, because there will be an intermittent cycle of this particular technology. So you need to be a little bit on the patient side. They can be used on superheated steam with the use of check valves. Pressure differential fluctuation should be understood, so the correct PCA or orifice can be selected for the proper operation. If you are controlling with a control valve, a zone, let's say for example a coil or a zone of coils that are heating air that's going over the top of a product, and the zone is controlled with a control valve. If that control valve will fluctuate, satisfy that zone, and all of a sudden we start to lose the steam pressure because we don't need the steam heat, then what will happen is we lose the differential that we actually get to process and help us push the condensate through the system. What we also do is if that pressure starts to degrade, we also lose the ability of that pressure differential to help us process that condensate that we have banked up through the particular orifice in that trap. So I need you to know what is the maximum pressure differential that one of these traps can see at its maximum condition and at its minimum condition. And I need you all to know Is the system modulating or is it constant? Is the system steam pressure constant or is it modulated? It's a tremendous question that needs to be understood, and you need to ask it. Very, very important. The next trap we're going to look at is a floating thermostatic trap. These traps are very, very good at low pressure differentials in processing condensate. So on a large heat exchanger, this would be a device that I would actually look at first, only because I know that in heat exchangers, again, as the temperature is being satisfied by the product because of the steam that we're putting into the heat exchanger body, then I'm going to degrade my pressure differential, and I have to have a trap that is capable of passing the condensate as it's formed, and many times it's a very good amount of condensate at a very low differential, and this particular trap can do that. These traps continuously discharge condensate. You see the float. This valve is tied to that float, so as the system starts and we end up building condensate, this float will cycle up and down as that condensate fills that body and process it. It's good for high capacities for its size. It's good at venting air. Inside the actual body itself is a thermostat. That's why they call it a floating thermostatic steam trap. That thermostat is setting there as a sentinel. When this trap is in a cold state and there may be air present, this thermostat will be open and it will process air and non-condensables. So that is a really big benefit to a float thermostatic steam trap, in that it really is good, and you do not need an external air vent if you use this particular type of trap. I will tell you that that thermostatic element will be a weak link. If you took a piece of wire between your hands, both hands, and you grabbed it and you started bending it, that wire over time would start to heat up and you would start to fatigue that wire. A thermostat that cycles just like a bellows or a bimetallic thermostatic steam trap that cycles, expands, contracts, expands, contracts, over time those will start to fatigue and you will end up seeing degradation and potential failure. And that's what will fail inside of this floating thermostatic trap, will be that thermostat. They're very good at handling variable and sudden fluctuations of pressure and flow rate. The components are now very resistant to water hammer. The steam lock release design of this trap is suitable for applications like paper drying cylinders where steam locking can occur. And pressure differential is very important to the capacity and the ability to process condensate with this particular device. Now, I have to tell you that these particular traps that I've showed you, the first two, are very good at processing condensate. But the one thing I want you to know is that none of the traps that we're going to discuss today have the ability to generate any additional pressure to help you promote the evacuation or the push, if you will, of condensate out of the heat exchange area. These particular traps are going to process condensate, and I need you to make sure that you position these steam traps so that we have gravity working on our behalf and allow gravity to help us allow the condensate to fall into the body and then to fall out of the trap and into the condensate return system. If you have to lift condensate to an overhead return header or to an overhead receiver, I want you to know that because I'm a pump guy also, and I sell, size, and help consult with pumping problems, on the steam side, we can lift condensate 2 feet for every 1 pound of pressure. So if I had a 10-foot overhead return line that I had to get to, I want you to know that you'd have to have 5 pounds to get to that 10-foot overhead return elevation. Now that doesn't, I didn't say that gave you the pressure to actually put that condensate into that return header, because I don't know what that return header pressure is. So you're going to have enough pressure, number one, to get it up to the elevation that you have to get it to, but number two, to actually get it into that envelope or that space. So whatever that pressure is, you're going to have to overcome to get that condensate into it. But remember, 2 feet, you can lift condensate 2 feet for every 1 pound of pressure that you have to help push it up the elevation that you want to climb to get it into that receiver or to the condensate return header. The next trap that we're going to look at is a thermodynamic disc trap. This is a very common trap inside of industry for drip main applications. And the way this trap works is really simply, as condensate is formed, we hold the steam inside of the steam space, and we're using the latent heat of vaporization out of the steam. And by the way, I want you to use the lowest steam pressure you possibly can inside of your process, whether it's heating, whether it's paper, lumber, regardless of the industry that you're in. I want you to try and always use the lowest steam pressure possible to get the job done. And the reason I say that is because what some of the good folks in the industry don't necessarily understand is that there is more latent heat of vaporization in lower pressure steam than there is in higher pressure steam. So if we have the ability, let's say, to bring 100 psi G of steam at 338 degrees, and we have the ability to knock it down and supply 15 or 30 pound steam to a heating application, I want you to know there is way more latent heat of vaporization in that 30 pound steam, 15 pound steam, than there is in that 100 pound steam. So I want you to be aware of that. And that is really, really, really important, because if you ever need help, you can email me, and Maureen will pass on some of my contact information for those of you interested. But I can help you evaluate that to make sure that you're using your steam reliably and efficiently. Many people get caught up that they actually need the higher pressure and temperature, and they believe they need the higher pressure, but what they don't realize is that they actually need it to help overcome the pressure differential of the system to get the condensate into the return. And that becomes a disconnect, and that will be something for a different time and a different discussion. This particular trap, as the steam gives up its latent heat of vaporization and it condenses, which is exactly what we're trying to allow it to do, the condensate moves into the steam trap body, this thermodynamic disc steam trap body, and it actually lifts that disc element, and it goes across the seat and out to the discharge. Now, if I put my thumb over the end of a water hose on the weekend when I was washing my car, and as I put my thumb over the end of that water hose, garden hose, the velocity would increase, and if I had the ability to measure the pressure would drop. And in steam, the actual latent heat of vaporization is the heat in BTUs per pound of the vapor, and the sensible heat in the liquid itself, in the condensate, is the actual heat in BTUs per pound of the liquid. Now I need you to know more heat in the vapor than there is in the liquid, but here's what I want you to know. If you take that liquid and you allow that liquid to fall in that liquid state to a lower pressure, what's going to happen is that liquid can't retain that sensible heat at that lower pressure. So what happens is there is a percentage of that liquid that will flash. A thermodynamic disc trap uses the properties of steam and condensate, and in this regard, the sensible heat in that condensate. So what it does is it manipulates that condensate as it flows across that body. It moves through an orifice, so it takes a pressure drop. And as it takes a pressure drop, that liquid flashes in that lower pressure, and that becomes the motive force to snap that disc back down on its seat and hold. So we end up using the property of that sensible heat in that liquid as we move across the orifice, take a pressure drop. The sensible heat cannot be retained in that liquid itself, and so it flashes the percentage or portion of it. That becomes the actuator modem that snaps that disc down. It's very simple. It works really well. They're very reliable. I will tell you this, though. It is machine surface, the disc and the seat, and you have to protect those with a strainer. And you see this trap, this particular trap with a built-in strainer. Those need, again, to be maintained and blown down so that we keep dirt, scale away from these, because as this thing cycles, and it will cycle per minute anywhere from 6 to 12, 15 times a minute, If it's machine gunning, then you could have dirt that has built up, scale between the actual disc and the seat, or you could have a trap that is just so worn that that you can't hold that actual steam in the space, and so it's called machine gunning, where the trap or the disc is just cycling, and you will literally hear it. You don't need a set of ultrasonic listening devices or a stethoscope. You can literally hear the disc from outside, even with earplugs and a hard hat on, and be able to hear this thing in a failure mode. Be careful about oversizing these things. I will tell you that if you have air in the system, this trap is okay for air handling, but what I do on this particular trap technology is I turn it into a horizontal position with that, let's say that strainer on the built-in body of this particular disc trap. I turn it up into a horizontal position, and that helps me to process air and non-condensables better with this trap technology. Okay, normally fails open, hammer resistant. They freeze-proof when mounted vertically. Dirt and scale can cause the trap to fail. That's why we have to protect them with strainers. A high back pressure affects the performance capacity. The traps are not recommended for low pressures below 10 pounds. So this is not a trap that you would use in a lower pressure application. But remember, there is no one perfect trap yet that I have seen, and that's one of the reasons why in those particular low pressure applications we would look at a different technology. We're going to look at thermostatic traps now, and there's two major thermostatic traps that we're going to take a look at. One of them is a bimetallic, the other is a filled element bellows thermostatic. And the filled bellows thermostatic has a N-propyl or isopropyl alcohol fill, so the actual vapor pressure of that fill is different than water. And so these traps follow the saturation curve of steam, but the one thing that they do is that there is many times, based on the way that these traps are built, there will be a subcooling of the condensate before these traps cycle. So it is possible with a thermostatic technology that you will have a small portion of your piping just prior to the steam trap. There will be a leg of subcooled condensate that will lay in there, and I have had nipple threads eaten out within 3 years because of this particular type of trap technology inside of a system. Now, the trap function, the system worked fantastic, but because of the actual ability to subcool, follow the saturation curve just underneath it, we subcooled that liquid, and we ended up having that degradation build up in that 8 to 12 inch section or zone just prior to the trap. So what would happen is that trap would cycle when it saw steam. It would close to trap that steam, hold it in the space, and it would cool, it would cool, it would cool. So it would bank that condensate up that would lay in that small zone, and that's where that degradation would be. These traps remove condensate at saturation temperatures and just below. They can be designed to fail closed or open. They're excellent at handling air. If you can imagine these traps in a cool, warming condition where we turn the steam on, but we don't have any heat yet, these will be wide open and they'll be evacuating the air non-condensables that are moving through the system. They are now made in water hammer resistant technologies. 35 years ago, they weren't quite as water hammer resistant. The filled bellows thermostats cannot be used on superheated applications because of that vapor pressure that I had discussed with you. And then condensate must be subcooled, which is the most important item that I would like you to remember for this technology. I want to go into sizing a couple different applications so you can see what we're going to be looking at. And a couple of the applications that I've chosen, one of them is steam main drip trap sizing. And what I wanted you to see is something that I believe is important from a safety as well as a capacity and a performance standpoint. In this particular chart, we're looking at sizing steam main drip traps and collecting legs based on a warming load and a running load. and I want you to understand this, that when the system is down, let's say during a holiday, let's say it's Thanksgiving, Christmas, whatever holiday you might have that the plant goes down, and you bring the plant back up, everything is cold, everything is insulated, by the way, and you've got, let's say, for example, a 10-inch steam main, and you're going to warm that steam main up. So you're going to take and fire the boiler, you're going to bring it up, and then you're going to put the steam into the system. With the collecting legs and all of the main vents open, you're going to put steam into the system. And I need you to know that the actual warming load at 300 psig, which I just chose that as an example, a 10-inch main is going to actually produce 322 pounds per hour of condensate per 100 feet. So I have been to a lot of plants, and I have asked folks if they use main steam line drip traps, because I can't see any. And I'll walk their plant, and I won't see any steam traps located on their steam main. And I need you to know your steam mains at running load and at warming load are going to produce condensate. And it's going to be up to you to evacuate that and make sure that you don't allow that steam to converge with that condensate inside that space or system. If this 10-inch steam line during warm-up can produce 322 pounds per hour per 100 feet, you can generate a lot of condensate on that startup condition. Now, what I want you to know is there is a running load when the whole system is up to temperature that is different than that warming load. So in a 300-pound steam system on a 10-inch main at running load, at running temperatures, the actual condensate generation ability of that line is only 85 pounds per hour per 100 feet. So I wanted you to see the difference on a warming load versus a running load. And I want you to know this, that in your facilities, when you start your equipment up, there is a much different load on that equipment than when you're at operational processing temperatures. So that's called the running load, and on the warm-up or startup, that's called the warming load or starting load. Okay, so big difference. What we're going to look at now is we're going to look at a safety load factor, and what we're going to do is we're going to calculate a couple different applications, and then we're going to apply a safety load factor. And I need you to know that I have a 600-page steam book that has all of this information in it. And as I was writing that book, there is a great deal of variance in safety load factors for steam traps. And what I did is I tried to pick the middle of the road safety load factors, but it depends on where you're located, what kind of system you have, what kind of environmental conditions you have, how well is your system insulated. And I do want you to know that I have seen a rash of problems when contractors come in and do any kind of work, and then they leave because everyone is so in such a hurry to get the system back up and running that they don't give the contractor time to put all of the insulation back on the system. And I need you to know that if that insulation doesn't get put back on that piping, steam piping, that it will drastically enhance the condensation generation ability of that system, and you may or may not be able to handle it with the traps that were selected with the insulation on. And unfortunately, I have a couple sad stories where people have died because insulating contractors ended up taking insulation off during a work outage, and the condensate steam traps that were supposed to handle the condensate load were not able to handle it during the time that the piping insulation contractors had stripped it to renew the insulation, and unfortunately they had an episode, an event, and lost their lives. So I need you to all be really, really careful and continue to be guardians of your facilities, that all insulation has got to be put back on. After the work is done, all the insulation needs to get back on, and if you do not have the insulation because they either took it, threw it away, or whatever, it needs to be repurchased and put back on. It's very, very, very important. The safety load factor, once we look at sizing a steam trap application, the safety load factor is nothing more than a number to compensate for the lack of exact knowledge about condensate loads that a trap will actually experience. So what it does is it covers our fanny, gives us the ability to make sure that we actually cover our fanny to get a trap that will work. In a drain point on a steam main, I wanted you to see this picture. I need you to make sure that you have a full diameter of that steam main that is being used as an actual condensation collection pot, so that we can make sure that as that condensates form, that we actually have a steam trap positioned with a full diameter leg, condensate leg, so that we can capture the condensate and then be able to put it back through that strainer and that steam trap. If you don't use the full diameter of that collection leg and you take and just weld a half coupling on that steam main, that condensate will fly right straight over the top of that unfortunate orifice that you put in with the intention to collect, but you will have a very difficult time collecting it. Okay, so please make sure that your collection pockets, condensate collection pockets, are the size that we need. So, a steam trap for a steam main every 300 feet of run, and use an SLF, safety load factor, of 2. When you look at trap loads, then you will see why your typical SOP procedure calls for drains to be open until you reach a specified temperature. Everybody's got an SOP that you follow inside your facility, and I want you to continue to follow it. If those have not been updated, I want you to ask your managers and your bosses to please review those, and to please, with the newer generation moving into a lot of facilities, I want to make sure everyone stays safe, and I want to make sure that those SOPs get re-looked at so that everyone continues to be able to go home safely. But let's just say that we had this 10-inch pipe at 300 psi IG, has a warming load of 322 pounds per hour, and remember, that's per 100 feet. So if we place a drip trap every 300 feet, it's going to be 3 times the 322 pounds per hour, so it'll be 966 pounds per hour for that 300-foot section of that 10-inch, 300-pound steam main. Now, if that's on a warming condition, warming load, and a running condition, we're going to have that 10-inch pipe, 300 psig, has a running load of 3 times 85 pounds per hour per 100 feet. And remember, the 3 is because we put a trap every 300 feet, so that's the 3 times the 85 gives us a load of 255 pounds per hour per 300 feet. Now, I have seen people that will say, well, Nick, I don't want to put a trap every 300 feet. I'll put one every 500 feet, every 800 feet. You know what? You can do whatever you want inside your facility, but I need you to know that when you turn that steam system on, you're going to generate condensate. So you just have to get ready. However you want to do it. You can put them every 500 feet, 300 feet, 800 feet. It's your choice. But I want you to stay safe, because I want you to know something. When condensate can converge with live steam, bad things happen. And I've seen it personally. I have unfortunately taught classes after incidents have taken place inside facilities. It's devastating, the damage that it can do. Trapping a unit heater. A unit heater is nothing more than a steam coil with a fan built into it. So one of the reasons I wanted to show this to you is that with the temperature starting to cool off, we're going to have unit heaters coming on. We'll have steam traps below. And I wanted you to notice a couple different things. On this unit heater, I wanted you to see I've got a vacuum breaker at the top of this. I've got, an air vent at the top of this unit heater. I'm going to tip and pitch that unit heater just a tiny little bit, and if you need to know what that number is, I have the numbers available. But it's really interesting to me, in all the steam equipment that I get to see, that condensate and steam main lines are many times piped dead level flat. They should not be. They should be pitched. Steam systems should be pitched. And people ask me what that number is. The U.S. government, the military, pitches their steam and condensate systems 3/8 of an inch per 10 feet because they want to avoid water hammer. You may not need to go to that drastic step and pitch it 3/8 of an inch per 10 feet, but I want you to pitch it something. And the typical standard would be 1/4 of an inch per 10 feet. You have a discussion inside your facility, but I would like you to consider pitching your coils, your steam and condensate piping to make sure we use gravity to help us drain. You'll see an air vent on the top of this air unit heater. You'll see a vacuum breaker on the discharge line. When we consume the enthalpy, the BTUs per pound out of that steam, we're going to collapse that steam and potentially create a vacuum in that space. The vacuum breaker helps us. If this steam system goes down of this unit heater, it will end up seeing a vacuum. That vacuum will hold that condensate inside that coil. If you have a platen press, if you have a dry kiln coil, if you have any kind of a blast coil or coil heating dryer, I need you to know when that system goes down, if you don't have vacuum breakers installed, it will be very difficult to evacuate that condensate that's being formed. You'll notice on the bottom of this, prior to that steam trap, the steam trap is the circle on the bottom, that the item just prior to that is the strainer. But I show 28 inches from the center line of that bottom header of that unit heater to the actual center line of the steam trap. And the reason I show that is because 2.31 feet, 27.7 inches, and I rounded it to 28, is pound gauge. 1 PSIG. If I have a small column, whether it's 1/4 of an inch wide or 10 feet wide, at the bottom of that column, if I put a pressure gauge, it would read 1 PSIG. So what I'm trying to do is make sure that you use everything you can to help you get rid of the condensate that's formed. And I like gravity. For a unit heater, I'm picking a size of the VN247. The capacity is 247,000 BTUs per hour, and it's really simple. You can go to the chart, and you can find these charts, and then I want you to go look at your steam chart. And let's say, for example, you're using 2-pound steam to actually use in your unit heater. It's got a latent heat of vaporization, BTUs per pound, of 965 BTUs per pound. So the simple math for this defensive lineman becomes this: 247,000 BTUs per hour divided by the 965, which is nothing more than the latent heat of the steam at the steam pressure we provide heater, is 256 pounds per hour. And then I want you to put a safety load factor on that number. The safety load factor is 3 to 4. And if you live in my area, in northern part of the United States, in Upper Washington State, we can see sub-freezing conditions. So I'm going to use a safety load factor of 4. So the actual steam trap that I would look at purchasing would be able to handle 1,024 pounds per hour of condensate. Okay. On a heat exchanger, the one thing I want to say about heat exchangers, and I think because I'm running a little bit behind, I'm going to move after this slide into our evaluation and trap maintenance technologies that are able to help us look at how we maintain these devices. I want to share this with you on heat exchangers, though. Heat exchangers have recently come to the front of my notepad because I've had multiple people call me recently with terrible problems with heat exchangers because of water hammer. And remember this, and I mentioned it before, if you have modulating inlet steam pressures, and you'll see on this simple drawing a steam control valve on the inlet side, but as it satisfies the temperature of that liquid on the outlet side, and we lose the steam pressure to help us push the condensate through this particular steam system, I am going to have a very difficult time getting that condensate wherever it is that we have intended it to go. And boy, oh boy, have I had a lot of water hammer problems recently with heat exchangers. So please be careful. If you experience any of those, shoot me an email, give me a call, and we'll discuss that. I've got some sizing for heat exchangers, and Maureen's going to make this available so you'll be able to go back through it and take a peek at it. But it'll give you an idea. This particular heat exchanger with 50 gallons a minute of water and the delta T that we're talking about using 15-pound steam has got a load of 7,935 pounds per hour. And the one thing I want you to be careful of is that I have 15-pound steam on this heat exchanger, and you size that steam trap at 15-pound differential, you're going to end up in deep trouble, because that steam pressure is going to degrade to the point where I want you to consider on any of the heat exchangers you ever touch in the future that you look at sizing those for a 1/4 pound differential to 1 pound differential, because you're not going to have a full 15 pounds on the heat exchangers that, unfortunately, that you get to actually maintain. So please, please be careful with that, and make sure that you use and be conservative as you troubleshoot those and you size the steam traps. This is nothing more than a simple picture of a vacuum breaker. I would like you to consider on every application you have using vacuum breakers and air vents, unless you've got a low pressure steam heating system where you're using vacuum pumps. I don't want you to use vacuum breakers on those, but on any of the rest of the steam heating equipment that you have, whether it's coils, whether it's platens, whether it's heat exchangers, I want you to make sure that you use properly vacuum breakers and air vents. And they're simple devices, they're invaluable, and you won't believe the actual processing ability of them. This is a picture of a simple strainer. I wanted you to pay close attention to this. At the bottom of this simple paragraph, it says this: for steam service, it is recommended that Y strainers be mounted sideways in horizontal lines to prevent the condensation accumulation. I went into a college one year. They were having terrible water hammer in a basement, and they said, we can't understand and we can't figure this out, Nick. And I looked at them, and all of their Y strainers had the actual Y straight down at the floor with the nipples and blowdown valves. And I said, okay. I said, well, listen, do this, and let's just try this. I want you to take every one of your strainers in this tunnel that has the water hammer issues, and I want you to turn the bodies of those strainers into a horizontal position. And the water hammer went away. So what it does is it actually gives us the ability to collect condensate and for it to subcool, and then that subcooled condensate reaches up and grabs the steam and collapses that steam. So that's just a little bitty simple thing, but it can make a big difference. Checking steam traps. There's a number of different ways, and I want you to know this is just a simple mechanic stethoscope. My friends at UE have fantastic equipment to follow up with them so that they have the ability to show you what the latest and greatest technology is to be able to maintain and monitor your steam trap population. I have used all of the different technologies you're going to see here, but I am not as up to date as an old defensive lineman that's degraded like some of the steam trap population I get to see. I still use and still have some of these older technologies. You place these on the discharge side of a inverted bucket steam trap. You can put them on a floating thermostatic. You're going to hear different things. If you take an ultrasonic, this is a 20-year-old ultrasonic device, you place this on a floating thermostatic steam trap. And let's say you're up to temperature. The thermostat will be closed in that F&T body. But what you hear is you will hear an actual velocity across that float orifice. So you will hear the discharging of the condensate. That's what you're going to be listening for. In a bellows-style bimetallic thermostatic trap, I need you to be very patient when you listen to those with an ultrasonic listening device. Be patient, please. It's going to take a bit, but you want to be able for that device to cycle. So it may take a bit for that actual steam to come through. It will actually shut the trap off. It will cool, and then the actual element of that thermostatic trap will open. So you need to understand how these traps actuate, and you need to understand that you are going to need to be a little bit patient as you listen to them and evaluate them. A thermodynamic disc trap is very easy to listen to and hear. So is an inverted bucket steam trap. Those are very, very easy to listen to and to hear with these devices. Temperature. I wanted to mention temperature. You can use temperature, but I want you to be very careful. Temperature only gives you one story. It'll tell you what the actual heat looks like across the zone of that steam trap, but it doesn't give you the complete full picture. And remember, these are mechanical devices. So I had one facility, one person tell me, Nick, I need to buy new steam traps. And I said, okay, really? He said, well, yeah, I shot it with a temperature gun and it's completely cold. I said, number one, is the steam system on? Number two, do you or have you ever cleaned the strainer out in front of the trap? He said, no. I said, put a hose on it, clean it, back flush it, and then call me back up and tell me what you find. He said, Nick, I don't need to buy any steam traps. The strainer was plugged. I said, okay, thank you. So I like to use a couple different technologies while I'm looking at steam traps. I will take a temperature gun or a thermal imager, and I will look at the heat across the actual application. This is a picture of just a simple thermal imaging camera, so I can look at the thermal image and the stratification of the vapor and the condensate in a steam application. But I love to listen to it. I love to shoot it with temperature, and I like to actually know, am I on? Is the steam strainer, has it been blown down? Has the steam equipment been touched recently? When was the last cycle of maintenance when had it taken place in the facility? So I know how old could the thermostats be in a floating thermostatic trap, an inverted bucket steam trap. Has it ever been pulled out? The strainers. I ended up sending a note to a large steam strainer manufacturer, and I said, how often should strainers be looked at? And this particular engineer sent me a memo back on his letterhead. And he said, Nick, he said, we recommend a minimum of 2 times every year, but he said, depending upon the pressure of your system, we would like you to actually blow your strainers down at the same time that you would evaluate your steam trap population. So I would like you to remember that and to be careful about those. This is a vibration analyzer. It's made by a company that actually, they called it a pen check, and what they did is they actually built this little device, and I want you to be careful of jumping in and buying a vibration analyzer to check your steam traps. You need to have a little bit of background, and you need to have a little bit of familiarity with steam before you jump in with a vibration analyzer to start checking your steam traps. This has not gained in popularity as much as the other devices like the ones that UE have available. I wanted you to know that this type of technology is available. But I also want you to know that you need some experience to be able to discern what it is it's telling you. If you're here today and you picked up anything, even one nugget, when I start a class, I usually try to tell the good folks that come, if you can just take one nugget away, whether it's you can lift condensate 2 feet for every pound, or whether it's you've got to be careful and make sure that you use vacuum breakers and air vents to make sure that you stay away from condensation-induced water hammer, then hopefully you will feel that this time was worthwhile. We will offer a discount if anyone's interested in the books that we offer when we teach our classes, and we also teach on-site and at neutral site locations across the U.S. So that is available for the good folks that were available today to listen to this old defensive lineman. I really, really appreciate it. Maureen, do you have any questions for me today, or did we come through unscathed with questions?
I'm sure people are still digesting the information. We did have one question that came in asking about how often you should clean and flush your strainers, but I feel like you just kind of hit on that right there at the end. But yeah.
Maureen, can I say?
Sure.
Can I say this, though,
Yep.
to answer that? It's dependent upon your system, pressure and temperature, and the criticality, if you will, of your steam system. So let's just say, for example, you run a low-pressure steam system, 30 pounds and under, that would be something that you could get away checking your steam traps and your strainers maybe once a year. So depending upon the pressure, depending upon what it is you're actually doing, the higher the pressure, the more frequently we're going to want to touch the traps and those strainers. But certainly I want those strainers to have a tag on them just like I do the steam traps, and I want them to carry just as much importance as the steam traps.
Awesome. Well, Nick, it's clear that you are just a wealth of knowledge on this topic. So if folks have any questions, or if you all are looking for any more information, his contact info is there. But you can also reach out to us, and we'll certainly get you guys hooked up. But I think we'll let everybody go from here and kind of spend the rest of the day thinking about this, and any questions, just send them our way. But Nick, thank you so much. We really appreciate it, and we'll get this recording up on our website because definitely lots of great information we want to make sure everybody has access to.